Okay, so this title I was given, Neutrino Mistakes, Wrong Tracks and Hints, Hopes and Failures. I thought about changing it to Fake News, but anyway, I stayed with the title Mistakes, even though that is a potentially offensive thing. Many of the speakers have thanked the organizers for inviting them. I actually approached this with some trepidation because talking about others' alleged mistakes is a way to make enemies. But we can find mistakes all kinds of places. I got this image off the front page of the meeting, and we have Enrico Fermi's thing here, where he says that the alpha is h squared over EC. And we all know that alpha is E squared over, that should be H bar C. So take 5 points off of Fermi and tell him to go ahead. I've actually heard 4 different stories about how this happened. You can ask me during the break if you're curious. Okay, I'm going to start with a report of muon decaying into a E and a gamma. This isn't strictly a neutrino experiment, but it's related to lepton number conservation. And when I was a graduate student, there was a rumor about this. It was in the mid-70s. The rumor was that the process had been measured with a branching ratio of about 10 to the minus 8 at the SIN facility in Switzerland. Now, the expected branching ratio is 10 to the minus 48 times these numbers that we now know, which puts it around 10 to the minus 60. Now, I never heard a talk about this, and a positive result was actually never published. They did publish a limit, and the limit is in this paper. They say no evidence for the existence of this process had been found. Now, they went on to, in the abstract anyway, to say that the measured positron-photon energy distributions are described by the decay mu plus, the E plus, nu bar gamma, and accidental coincidences. Whether or not this was the actual source of the rumor before they'd taken that into account, I really have no idea. But the confirmation of my memory of all this was confirmed by a recent discussion with Robert Schoch, and he led me to a paper by Bjorkane and Weinberg, Mechanism for Non-Conservation of Muon Number, where they just talk about that generally. But there's a footnote in there that says it would be disingenuous for us not to acknowledge that our interest in this question was kindled by an experiment now in progress and by rumors of a positive signal. So I don't know if that's how you publish your rumors or not, but again, it was never published. The important thing for me was that this rumor led to a series of lectures about lepton number at Fermilab that was given by Robert Schrock, who was a postdoc there at the time. And that's actually where I learned about neutrino oscillations, because that was a main part of the lectures there. Okay, so now an outline of my talk. I sort of categorized a large number of mistakes that I could find. Various people sent me their lists. And you know, I just accumulated my memory of various things. I'm going to talk about the ones in red. If anyone brings up any of these other things during the discussion, I have one slide about each of the others, but probably you'll bring up things that aren't even on any of my lists. Okay, so what is a mistake? Is it a statistical fluctuation? Or probably maybe systematic error? A wrong interpretation of good data, or just a theoretical misunderstanding of something? Well, defining a mistake should be very important for this talk, and actually I spent some time thinking about it, but then I gave up. So I'm just going to go with my list, and we'll see. There's really no good definition. It's kind of related. So one thing might be, is a wrong theory a mistake? I think we pay theorists to come up with mistaken theories. We want to have as wide a number of things as possible. So, a bad theory, none of those are on my list. If we if the IMB bag collapses or if the Super K tubes all explode. That could certainly an experimental mistake, but nothing like that ended up on my list. There were all sort of mistakes of understanding, but again, there's just no threshold for what one might consider. Was dark matter to explain omega a mistake? I mean, that certainly fits well the category of wrong hopes and failures and, tracks. That was a great idea at the time and just ended up not being the correct explanation of the dark matter. So that didn't make my list. I will say that going through the lists, I looked sort of for common threads and things. And, I'll report now that I really didn't find any. Every story that I'm going to tell is just a little bit different. Maybe, again, during the discussion, someone will be able to identify some common threads to all of this. So let me go on. Okay, I'm going to start with a 17 keV neutrino. And here's sort of a timeline for some of the things that happened. In 85, Simpson noticed a kink around 1.5 keV in some tritium data, which corresponded to that mass for the neutrino with a probability of about 3%. This was followed by various negative results, but then Hyman Simpson looked again in 1989 at sulfur 35, found a kink near the same place, a little smaller probability, and then they sort of dived into it and published 2 measurements in sulfur 35 in 1991. I'll put the references that I found off to the right here. And that led to a number of experiments. Now, sort of the definitive exclusion, I think, is generally accepted to have come in 1993. And that was this experiment, evidence against a 17 keV neutrino in sulfur decay, where the data is listed here and a 17 keV with the published attributes. The data would have fallen along this curve there, and obviously doesn't. The force behind this experiment is often attributed to be Stu Friedman, who was one of the members here, 4 institutions. I think that's a record for what I've seen. But he sort of was loudly complaining about the other experiments. And the other examples that I found of mistakes, there weren't really sort of antagonists to the results. I mean, the more common thing is that mistaken things just get ignored and forgotten. But anyway, this was a case where there was sort of an explicit person arguing against it. Okay, but then in 1993, one of the authors here actually identified some effects which were likely responsible for their result, although not necessarily generally. And I'll show that here. This was the original data. This was his reinterpretation with a more complete electron response function, including something called intermediate scattering, as the electron did things before you actually measured it. When he put in that response function, the data looked like this and had, the evidence that they'd previously reported was lacking. This doesn't necessarily explain all of the results, but some of the other positive experiments happened in the time. But anyway, the consensus became that there was no 17 keV neutrino. So just a personal comment for me. Some of you know that I put out this newsletter every month. The last days of the 17 keV neutrino was sort of coincident with the first days of my newsletter. And I found at the time that there was much more theoretical interest in this than in atmospheric neutrino oscillations in the range that they ended up being by a factor of 5. So when I was trying to find references to things that might be related to what I was interested in, atmospheric neutrinos and long baselines, it ended up being all about possible explanations of that. Maybe it was just more interesting because you had to do more to get it. But okay, the next thing I want to address is Klapdor's neutrinoless double beta decay. This came from the Heidelberg-Moscow collaboration looking for neutrinoless double beta decay in germanium-76. Now, there were actually two publications, both of them in 2001. The first one occurred in this journal. It had 14 authors. It put a limit on neutrinoless double beta decay of about 210 to the 25 years at 90% confidence level. Several months later, another publication came out, and for me, something rare happened here is that the preprint and the publication came out the same day. On this, there were 4 authors. There was a positive signal, as shown here. The lifetime was 1.5, 10 to the 25 years at 95% confidence level. And these are the 4 authors. So it was a portion of a collaboration. Now, a lot of my colleagues looked at that and said, I don't see a signal. Actually, it's not quite that bad because you do know exactly where to look. And if you looked exactly where you looked, there was a peak there which they claimed was a signal. Now, soon after that, there was a early reaction with a comment that appeared in a preprint. It was eventually published. This had, 15 or so authors. And they wrote, "We comment on the recent claim for the experimental observation of neutrinoless double beta decay. We discuss several limitations in the analysis provided in that paper and conclude there is no basis for the presented claim." Now, I'm not going to go through any of the arguments. I'm just going to say that this represented the average reaction of the people who knew anything about this, i.e., they didn't believe it. So when Professor Yarskag tells us the first day it's not belief that matters, I think belief actually does matter a lot as to whether we're going to consider something a mistake or whether we're going to consider it right. Anyway, they didn't believe it. They listed a bunch of reasons why. So from a personal point of view, when the first result came out, there was a theorist I didn't know from CERN who sent me notice about it. So I put a little notice in my newsletter that they'd reported this, evidence for neutrinoless double beta decay, and what the mass and lifetime were, the links to the preprints, and also I had there an earlier link to the preprint based on 125 grams of germanium-76. I quickly got this email from John Beacom, who said, "This is nonsense. This has to be nonsense. This shouldn't meet the standards of your newsletter." So I replied, I didn't have standards. I had deadlines. And he really enjoyed that comment and quoted it back to me about 10 times over the years. Okay, then the next month, I reported on it's 26 authors had this comment. Okay, so I reported on what they said with the links. And then I got a long email from Clapdoor. "I'm surprised to see that you handle the comment put on the web on the same level as my published paper." And he says, "I propose you take this unserious comment out off your webpage." So I responded to him that my newsletter gave equal attention to the discovery of neutrino oscillations and a novel about a Neanderthal neutrino physicist who somehow ended up in the middle of the snow detector and did some interesting things. He actually never subscribed to my newsletter. So. Okay, so going back to the believability, there are a number of things that just sort of led, I think, in my mind and to other people's mind, to why we didn't believe in this result. And a lot of them sort of don't directly access the physics of the result. But a key thing, I remember the one talk that I ever heard by Clapdoor, he got in a big argument with other members of his own collaboration. And it seemed clear to an outsider that they weren't sharing data with each other. And that just seemed wrong. And my most favorite quote in all of physics, Doug Michael from Caltech came out of that meeting and he said, "Even if it's right, it's wrong." I think all of this collected to me, here was the upside down test, I don't know if you, It felt like a posteriori analysis, and so I don't know what they did wrong, but again, for a long time we don't believe it. Now, an interesting thing happened, I think. Even though few in the community believed it, it became a benchmark. So in the EXO publication on their finding limits for neutrinoless double beta decay, the Goethe one in 2013, here's Kamlan Zen in 2013, they all specifically mention their limit compared to the reported limit there. So that can happen. Okay, the next topic is superluminal neutrinos. I think most of us, even at the time, thought of it as a joke, so there were a lot of good jokes. I'm going to go back to actually Minos. Let's see, Minos did a search for the time of flight of neutrinos back in 2007, and we published our preprint in 2008. Now, we unfortunately live in a field, or maybe it's fortunate, I don't know. Most of us, particularly the collider physicists, haven't read a majority of our own papers. This was one Minos paper that came out in 2007 that I hadn't read till 2011. And in it, we actually have sort of a 2 sigma superluminal result. Now, what we were doing was just measuring the time of flight of the neutrino and looking for a delay that might have been caused by a massive thing. It wasn't sensitive at all to the interesting regions of mass for neutrinos. It was up in the 50 MeV range, but it was just something that sort of had to be done, so we did it. Now, this result was compared quite extensively in the opera preprint, which was quoted as 6 sigma. On the same day, there was a CERN seminar broadcast that was actually live on the web. This was the first time I ever watched a seminar or a podcast or anything like that. And so we were having a collaboration meeting at Fermilab, and we stopped to listen to this broadcast, and it was very interesting. The same day, CERN issued a press release. And then soon after that, the popular media was just flooded with stuff about Einstein being wrong. This was the abstract of the preprint, measurement of neutrino velocity with the operator detector and the CNGS beam. Let me say from the outset, I don't think Opera did anything wrong. They had this result, they didn't understand it, they sat on it for months, they tried to figure out what was going on, and then they presented it publicly. But in my mind, there was a mistake. Let's see, even though I hadn't read our own paper, I got invited to give a talk, so I went back and read our own paper, and then made some comments at some talk about the Opera result. No neutrino's velocity was measured. There were 3 ways to make a mistake with clock surveying or something about the beam physics assumptions. But I made a comment that I thought Opera was wrong, although I didn't know why. But if Opera was right, we don't know what it is, so the next experiment to test it wasn't obvious as to what it is that you could do. So that we'd have to wait for theorists if it turned out to be right, and we didn't have that framework at the time. This was the press release. Again, if you read through the CERN press release, nothing here is outrageous or wrong in my mind. To me, the problem is the existence of this press release. I don't think that should have happened. I'm going to go to some Gedanken history here. Because after the press release, this just made front page news all over the world. Is Einstein wrong? Faster than light particles, tachyons. People were wild. But suppose Opera had had the same seminar, but CERN had not issued a press release. Okay, I just reconstructed in my own mind what would have happened. 2 weeks later, there would have been an article in the science section of the New York Times about this, and we all would have winced, but this wouldn't have happened. The scientific story would have been the same, the worldwide fuss would not have been the same, and then Opera, went back and did their due diligence and made the revised preprint and by 25 February announced that the possible loose connector was responsible for most of what was going on. So that's sort of what's going on with that. Okay, the next thing I'm going to talk about is probably a little bit more controversial because some people still think that light stereoneutrinos exist. But I'm going to put it on the list of mistakes, LSND and EV stereoneutrinos. Okay, so here's a partial timeline. I first heard about it at Neutrino 1994. It was announced with 8 events with a background of 0.9 from LSND. The first paper occurred about a year later with 16 events, much bigger backgrounds, and statistical and systematic excess. When this paper actually appeared, there was another paper in the exact same journal from a single person's analysis of the exact same data. It was James Hill. Now, he was actually working with Al Mann, who didn't sign the paper. I think Al Mann was really the impetus behind the second paper, but wanted to give credit to his student who had done all the work. So anyways, this appeared with a single author. 5 events from LSND with a background of 6.2. This was sort of what we would call a thing where you look at the correlations between all the variables. Here he just made a lot of cuts, but it was the exact same data. So he set a limit. Okay, this motivated the mini Boone experiment, which in 2007 opened up their box on their blind analysis, and Fermilab issued a press release. Mini Boone results inconsistent with the existence of a stereoneutrino. Now, what happened was they had previously determined at what energy to look for their signal, and above that energy, they really didn't have anything. Below that energy, they did have a big excess compared to what they expect. So that got called the low energy excess and wasn't called an oscillation signal. And by the way, this is sort of the best fit from the original paper of LSND as to what they were looking for. And I just remind everybody, they weren't looking, when LSND was built, they weren't looking for stereoneutrinos. When LSND was built, they were looking for what we now call theta 1-2. It wasn't universally recognized that solar neutrinos were due to oscillations. But anyway, they were able to put that limit on, put that region on based on their alleged signal. And then some other anomalies came along, the gallium anomaly, which has been mentioned, the reactor neutrino anomaly, which we'll probably hear a little bit more about a little later in the meeting. Okay, now there are a lot of issues having to do with light stereoneutrinos, and it's not my goal here to tell you why I don't believe it. Maybe you do, maybe you don't. These are many of the issues that I think affect the believability of this as having something to do with light stereoneutrinos. That is not to say that there isn't something going on, because there is something going on. There are a number of anomalies. The question is, does it make any sense to fit them in with stereoneutrinos with what else we think we know about the neutrino? My answer is no, but others certainly will be different. This is an example of a recent updated global fit of short baseline experiments. I think Junti is one of the main leaders of this group. And they look at the various parameters and they find a best fit in these regions of parameters, which in their view is therefore consistent with the existence of light stereoneutrinos. A problem is that this best fit is a terrible fit. So I came up with this little nugget here, which I'd love to repeat. Why physicists disagree. If the data doesn't agree with the null hypothesis, and it doesn't agree with the alternative hypothesis, some say you need more data. I say you need more hypotheses. Okay, something interesting might be going on. LSND, mini boon, gallium, might be the same thing, might be different things, might be interesting, might be uninteresting, but it just doesn't appear to be sterile neutrinos. Now, if your job is to say that sterile neutrinos might exist, then you're going to say sterile neutrinos might exist. So this is a recent article from Joe Licken who says, there's much more evidence now for sterile neutrinos, and we're going to study it at the Fermilab Short Baseline Program. I could be way wrong here, but I don't think that any of the people working on the Short Baseline Program think that 3+1 sterile neutrinos exist. I think they think something might be going on, and these are good experiments to do, and therefore they're going to do them, and they aren't going to tell us what they think is going on because the theorists haven't come up with enough good models yet. But again, my view is that it's been ruled out for a long time. The anomalies themselves are real. They may have interesting or uninteresting explanations. You might, if you don't know what you're looking for, you might find it, you might not find it, but you can't rule it out. Okay, next I'm going to go to something which actually I was a little surprised has been mentioned twice here in this meeting, although very quickly. And that was this oscillation limit published by IMB based on the ratio of upward-going stopping muons from atmospheric neutrinos to upward-going muons. And this was the paper. I think Paolo showed it. This was the limit. And this little blue region is where we now exactly think that neutrino oscillations exist. So it's sort of right in the middle of this limit, which says that they don't exist here. And the interesting thing from my point of view relates to something that was in Gary's talk when the program, the Scully panel was comparing the Brookhaven experiment to the Fermilab experiment for long baseline. There was a difference in the delta M squared reach, and that difference was mostly in this region. So Al Mann presented this as evidence that you didn't need to cover that extra region in the long baseline experiment because it had already been ruled out. Okay, now retraction was never really published, but the limit was apparently quite sensitive to structure functions, I'm told. The closest thing to a retraction was this 1999 Cosmic Ray Conference abstract, Neutrino Oscillation Analysis of IMB Upward-Going Muon Data with Improved Interaction Model by a subset of the collaboration here, where they said they were going to look at this, but then the full article never actually appeared in the proceedings. All we have was the abstract. Okay, now I'm going to go on to what I'm calling God's mistake. Okay, now a similar slide to this was shown by John Learned. There's a whole bunch of happy coincidences in the neutrino world so that we were able to do all these, find delta M squared, theta 1, 2, delta M squared, theta 2, 3. This slide was actually prepared in 2005. I stole it from Stan Wojcicki, who stole it from someone else. When I asked him who, he said he forgot. So someone out there gets credit for this, but it's called The Intelligent Design of Neutrino Parameters. And again, these have probably all been mentioned. Let me just mention that theta 1,3 at the time was known to be small enough so that all these things could be done with 2 neutrino experiments. Now we know that all the mixing angles are large. How is it we get by with 2 neutrino experiments? It's because theta 1,3 is small enough that 2 neutrino formulas work for most of the things that we do. But at that time, he said the acid test is, will theta 1,3 be big enough to see CP violation and determine the mass hierarchy, thus proving that we have intelligent design of neutrino parameters, because that happened. So how about, extending that a little more? If I extend it a little more, I'd say I want delta around 3 pi over 2. That gives us the biggest possible effects. I want the inverted hierarchy, so we can tell Dirac and Majorana from neutrinoless double beta decay, maybe the beta decay endpoint, and Majorana neutrinos. And this one seems to be wrong. I mean, there's increasing evidence we live in the normal hierarchy, so maybe God's made a mistake, or maybe God knows something that we don't know why. That's really a good thing. Okay, so what are the common lessons from all of this? Again, I didn't really find us any. We all know failure's a great teacher. We learn from our mistakes. Is there a role for critics of experiments? Well, the most prominent critics, Morrison for solar neutrinos and Miyake for atmospheric neutrinos, I think didn't do us much good. Stu Friedman did. But active skeptics haven't really fared very well. Let me just repeat some of my own thoughts about some of these issues. There's no theory of systematic error. That causes a problem in extracting them. There's an infinite number of tests of the null hypothesis. So when you rule out the null hypothesis one way, maybe it wouldn't be ruled out some other way. You have to know what you're looking for. You can't really prove anything in physics. I think we all know that, but I just think we should be careful using the word proof. The union of two confidence levels isn't a confidence level, and I'm no fan at all of the 5 sigma criteria. I think it's applied because of a misunderstanding. Okay, let me just address that briefly. You have a null hypothesis, an alternative hypothesis, a test statistic. You calculate a chance probability. All of this is only valid if the hypotheses and statistics are specified a priori. But we have to do a posteriori analysis all the time. We get our data, we see something unusual, we have to look at it. We say it's a 5 sigma effect, that the events weren't coming in time or something. That's totally a posteriori. You don't know how many other questions you could have asked that would have seemed just as unlikely if you had seen them, but you didn't because you didn't. I cringe when I hear people say, I've seen so many 3 sigma effects go away. And I think most of the time those things are called 3 sigma effects because you calculate your a posteriori and a priori statistics exactly the same way, but the a posteriori ones don't have meaning and the a priori ones do. So I've never seen an a priori 3 sigma effect go away, and I predict that in the rest of my lifetime I never will. Okay. Summary and conclusions. Somehow, even though our field does a poor job, I think, of preventing statistics, I think we do an excellent collective job of taking seriously the effects which turn out to be right and being skeptical of the results that we don't. So somehow we're all smarter than what we can say. Okay, and again, calling a result a mistake has a connotation of criticism, so I do not criticize the vast majority of these reported events. I'm solely responsible for all the mistakes in this talk about mistakes. I did get help from these people I want to thank, and I do have this other list if the discussion takes us in the direction of any of these. Thank you.
Thanks for this very interesting talk.
I think you have misunderstood me, because I'm saying belief is not a physical concept. Because you see, believe, is it 100%, less than that? Because we have to have something quantitative in order to make it physical. So you see, we don't say that. It would have been better if we had a different word for it. You see, that's what I mean. When you say I believe or I don't believe, what do you mean? I believe, I don't believe.
Okay, well, I think what it means when we have a paradigm, those are the assumptions, the things that we believe. They may be wrong, the paradigm might change, but you need to start with that, and then you discuss the things you know might or might not be true, and discuss the things within the concept of that paradigm.
But also the belief then, but then you have to give me a number. You see, you have to give me a number. This is a working hypothesis, and the probability of it being correct, in your opinion, is 0. Or is it 50%? Or is it 20%? I mean, we don't have a word for that. You know, that's my problem. When people say, "Oh, it's so easy to believe or not to believe," it's so very, very easy. But it's much more difficult to specify why you believe or why you don't believe, and you know, things like that. And I think as a physicist, we have a duty to do that.
Okay, well, again, in physics, you can never be 100% about anything.
Maury, can you go back to the IMB, the plot? Because I want a disclaimer to start out with. No, the plot, yeah. I would like to say I had nothing to do with this, but that would be slightly unfair because the IMB1 curve is mine. But that came years earlier. And there is a very significant story behind this, and I had nothing to do with the rest of it, but I was responsible for that. And the reason this was done is because we were absolutely desperate to try to determine some energy or distance dependent to what was known at the time this paper was written. And this actually reflects a very, very good idea. And the very good idea was to try to access that energy range that would not be contained in the detector, but you'd be able to be sensitive to it by looking at the edge of the upward going muon. So it actually was conceived very nicely, really a very good idea. And that was good. The execution was somewhat flawed, but I believe the execution was somewhat flawed because it did something which was known to be risky at the time, which is it combined the high energy Volkova flux, which was fairly well understood, with a lower energy flux in order to span that gap. The low energy flux they decided to use here was the Lee and coflux, which was eventually known to be wrong, published in 1996, that there was a mistake in it. So the problem you got into here was a good idea, it was conceived well. The data, according to Larry, the data is actually consistent with super-K, so the actual measurement was correct. But the interpretation was damaged because the fluxes that were used were wrong. So,
Okay, well, again, just my comment is that I don't know whether anytime you publish a mistake there should be a retraction or not. But again, this was the closest that happened for that.
okay, all right.
Just a small comment, Christian Spiering, Daisy, on your remarks about Klapdor and about neutrinos faster than light. In the case of Klapdor, of course, many people used it as an argument to the funding agencies, right? Still, they did not believe, but they wanted to check it. And a similar thing happened to us in IceCube the day when the faster than light neutrinos came up. That was a IceCube meeting in Sweden. Everybody was looking to the press conference, and after that we had lunch, and during lunch already the idea came that we could test it. We could test it by looking to downgoing muons, which are accompanied by a neutrino interacting in the detector, and the muon comes a little bit later than the neutrino. It's a 1-2 nanosecond effect, very hard to check in IceCube. And thanks God, the claim that it is, the answer that it is wrong came before we invested too much PhD time into studying that. Right.
Just in a similar vein, of course, Minos decided to do it again with much better timing. And by the time we'd gotten very far, the claim had been retracted. So, but, we had spent some money. So it took another 2 years to get the paper out. I don't know if anyone ever read it.
Peter Vogel from Caltech. I want to make comment on your discussion of the Klapdor result, and it's more general how to approach such situations. So when Klapdor first makes a claim, we wrote this so-called commissar's note. That was, you flashed it there. I am among the authors, where we pointed out what we thought were weak points in that argument. But then much later came papers which actually had some new results. That was your next transparency, like the EXO paper. And we mentioned there that it excludes the Klapdor result. And from your talk, it sort of looked like you are criticizing that we did that.
No.
I thought you are on PDG, I am on PDG. Things which are in referee journal, which Klapdor's result was, are supposed to be open to criticism, and that result showed that club door cannot be right because what was measured contradicted that. And I think it was our duty to do that.
Sure, sure.
Lee Grodzins. I just want to make a comment from the point of view of the reviewer of such a paper. I was a reviewer for Simpson's paper, and I knew him. And I wrestled a lot with that. I can still remember it. And I finally sent in my review, and I said, I don't believe this at all, but I cannot find anything that he didn't do that I would have done as checks. And I think that I actually called him. I think his first name is John, isn't it? Yes. Yeah, and I had a discussion about it, because I said I'm a reviewer and I really don't believe this result. And we went through it again, and so I said, I recommend that you publish it, and other people will check him out, because I can't find anything wrong. I think that the question for a reviewer is an interesting one.
I wanted to make a comment, adding one error or problem, which is the Mont Blanc detection, the LSND detection of the supernova 97A, which actually has created and still has a literature to that paper. And I think it's an interesting result. I wanted to add one more comment.
But that's gravitational waves, right?
Yeah. With the supernova, and they detected 5 neutrino 4 hours before the IMB Kamiokande event.
Oh, okay.
So
Okay.
during the Adam Barrow's talk, there was a very quick reference to that problem. But I wanted to add one more comment. So actually, De Ruhula wrote about it. There's been speculation, double bang in supernova and so on. So that one result, which actually in my view is a genuine fluctuation in the result. They were, the Claptor, so that's what just adding on the list. I think this to me was one of the most interesting errors in my life of a neutrino physicist. I wanted to add a comment about Claptor, but and there is to me a methodological problem on this, and is when a collaboration splits, breaks down, and a fraction of the member of the collaboration publish a result when some of the collaborators do not accept the result. And this, for me, is very problematic. Now, on the supernova event, there is the Baksan, there have been 3 detectors. Also, the Baksan scintillator detector published a result, which is published first on JetP and then on Physics Letters. And this result is being published by only 4 authors, Alexeyeva, and 2 other persons. And a number of prestigious scientists, including Chudakov and so on, didn't sign these results. So I will not comment, but I was very disturbed by this result. Actually, I think Adam Burrows did not comment. If you do the analysis of the supernova with 3 experiments, namely Kamiokande, IMB, and Baksan, or if you do it with just 2 experiments, which is IMB and Kamiokande, well, the results are actually quite similar because the errors, but still, so anyway, this is just, the point to me is that the scientific community should find standards in cases when a collaboration cannot agree and only a fraction of a collaboration publish the results. Because the authors, actually even in the opera paper, there is a famous question that the numbers of collaborators did not sign the paper, but did not, and so this question, I think to me is important for
Can you come to a close or wind up? Yes. that was a nice speech, but...
And of course, the opera paper was never published.
Sorry, we have an order here, so there's a chair and there is an order in this conference. No? Otherwise, we make mistakes.
A little follow-up on Klapdor. There is one further aspect, and that is dishonesty. He was submitting his paper to a European Physical Journal, and during the process of evaluating the paper, he was submitting it to an obscure journal in Singapore, which was accepting that within a fortnight over Christmas, not waiting for the time to get the turned down by the journal, by the EPJ. So, in my opinion, that is a dishonest behavior.
Yeah, I was told he was an editor of one of their journals.
Daniel? No.
Didier Vakin from LAP. In your list of mistakes, you don't mention the Davis trying to detect neutrinos from nuclear reactors. So is it because you don't think it's a mistake, or it's at the frontier of the definition of your mistake?
I'm not familiar with that.
I was talking about Ray Davis trying to detect neutrinos from reactors with a chlorine. It was only a rumor, or there was some real try.
I remember someone taking Davis's data and saying they see 17-year cycles in it once or something, but I don't think that was him.
No, he looked for neutrinos from a reactor and should have achieved a null result, and he published a null result. So
Okay.
you could say it was not, in hindsight, a good experiment to do, but it's not a mistake. I mean, it turns out, from the point of view of neutrinos versus antineutrinos, it is a good experiment to do. So I'm not sure what the mistake is here.
So as far as I can see, while reading some of these papers, it motivated several theorists, of course, Pontecorvo being one of them. It also even motivated Pauli to look at lepton number, because these things were about to be measured by Ray Davis. Now, there is supposed to be a rumor, but I never could track it down. And the only thing I saw was that there was an account in some bulletin of the American Physical Society, or something like that, saying that they didn't see anything. And that was it. So there was no mistake whatsoever.
Hi, Adam Bernstein, Lawrence Livermore National Lab. So Maury, in the beginning, you asked if you might discover a theme within the various topics that you laid out. And I just thought of one that may be useful, which is the difference between productive mistakes and unproductive ones. An obvious productive mistake is like leaving the uranium ore in a file cabinet with a photographic plate, and that generates a whole series of exercises that bring us to the modern world. An unproductive one might be the example of the opera result, which basically a press release was put out, lots of sound and fury, but no kind of anything that followed from it. And so I like that categorization. The only difficulty is you don't know whether you're making a productive or unproductive mistake a priori. So let me leave it at that. Thank you.
The opera wrong result made neutrinos known in every village on this earth.
I just agree completely with Sergei said. It made me a very popular grandma, very much so. My grandson, Grandma, you know neutrinos go faster than light. And the classmates, they all contacted me. They wanted to know about neutrinos. Of course, they didn't know what a neutrino was, but it really excited the society. So I think maybe they should have had some medal for that. I don't know.
Yes, we need more mistakes. So, Michel.
No, I'm sorry, but I really disagree with that. Because, I mean, especially in our world, now the quotation index is made probably very high for Klapdor, for Dama, for experiments like that. And I think it's really unfair. I mean, to publish a stupid result which is quoted much more than good results is awful.
Well, just to comment on wrong results having positive consequences, just think about the LIGO business, which I think would not have been there if it weren't for Joe Weber. All of us remember Joe Weber's soon shown to be wrong claims of seeing gravity waves many, many years ago, and it boosted the industry. People got money, and so wrong results can have really wonderful consequences.
Can I just make one rejoinder on the earlier comment, which is the productivity part in the example that this gentleman gave is productivity of attention to the scientific community, which is of course valuable, but the productivity I was talking about is scientific productivity. Does it lead to some advance in the scientific community? So of course it's great that we all have, indeed I have many experiences of people, the only time my family ever paid any attention to my work was when the opera result came out, so I'm very sympathetic with that. But it's not the same as a scientific advance, so I just want to make that point.
I also want to say that I disagree with the opinion that a big press reaction is enough to justify publicating wrong results. And there is a very nice article from Jan Konrad from Sweden. Don't cry wolf. You cry it once, you cry it twice, and the third time nobody will come and help you against the wolf. We can do it without a big effect in our field. But what when the people do not believe in climate change? And that we have also to consider.
I agree with that comment.